It sends out these test patterns and pictures in color and black and white. 15,000 to 25,000 tube samples can be tested here at one time.
It's 1869. Two German physicists, Julius Plücker and Johann Wilhelm Hittorf, are experimenting with vacuum tubes in their lab. Suddenly, they saw something strange, a mysterious glow inside one of the tubes. They had no idea what it was, and after studying it closely, they realized those glowing rays were actually streams of electrons. They named them cathode rays, and the tube producing them became the cathode ray tube, or CRT. At that moment, they didn't know they had just discovered something that would change the world. That flickering glow was the beginning of the screen. One of the most important inventions ever happened in Earth. Now, it's everywhere, from the device in your hand to the towering billboards of Times Square. The glowing screens that define our world have come a long way. And now, we'll take you back to the past, so that you get to know how those cathode rays turned into the modern displays we see today. Well, the table turned around. In 1897, another German physicist, Carl Ferdinand Braun, built on this theory and invented the first CRT display, which became known as the Braun tube. This device worked by directing electron beams onto a phosphorescent screen, creating glowing images. While Braun's invention was initially used for scientific experiments, it would later revolutionize televisions and computer monitors, remaining the best display technology for almost a century. Braun's contributions were so impactful that he won the Nobel Prize in Physics in 1909. Another major advancement came in 1907, when Boris Rosing, a Russian scientist who worked with Vladimir Zworykin, one of the pioneers of television, used a CRT to transmit simple geometric images to a screen. Although this early attempt at television was primitive, it demonstrated that electronic screens could be used for broadcasting moving images. The true commercialization of CRT displays began in 1922, when manufacturers started producing them for early television and computing applications. Throughout the 20th century, CRT screens became the standard for TVs, oscilloscopes, radar displays, and later, personal computers. By the 1970s, most computer monitors could only display green text on a black screen, but by 1990, IBM introduced the Extended Graphics Array (XGA) display, which could show 16.8 million colors at a resolution of 800 by 600 pixels. These early screens may seem outdated by today's standards, but at the time, they represented technological innovation. CRT technology held up the market for decades, but as we'll see in the next section, the world of displays was about to change forever with the invention of plasma, LCD, LED, and OLED technologies. The journey from bulky CRTs to the slim, high-definition screens we use today was just beginning. Every time you look at your smartphone, watch a movie on your television, or work on your laptop, you are engaging with display technology. But how do these screens actually work? At their core, displays function by manipulating light to create images. While different technologies such as LCD, OLED, and e-paper have unique ways of rendering visuals, they all rely on fundamental principles like pixels, refresh rates, resolution, and color rendering. A display is made up of tiny elements called pixels, short for picture elements. Each pixel acts like a tiny dot of light that can change color and brightness to form the images we see on screen. Pixels are the smallest controllable unit of a digital image, and when combined in large numbers, create high-definition pictures. The more pixels packed into a display, the higher the resolution, meaning sharper and clearer images. For example, Full HD 1920 by 1080 pixels contains over 2 million pixels, while 4K 3840 by 2160 pixels has more than 8 million pixels. Modern high-end displays like 8K resolutions push these numbers even further, exceeding 33 million pixels for an exceptionally smooth viewing experience. A display's refresh rate determines how many times per second the image is updated. This is measured in hertz. Most standard monitors have a 60 Hz refresh rate, meaning the screen refreshes 60 times per second. However, Gaming and high-performance displays can reach 120 Hz, 144 Hz, 240 Hz, or even higher. The higher the refresh rate, the smoother motion appears, which is crucial for gaming, high-speed action videos, and virtual reality applications. Another crucial factor in display performance is color rendering, which refers to how accurately a screen reproduces colors. Displays use different color spaces, such as sRGB, Adobe RGB, and DCI-P3, to ensure precise color accuracy. The most advanced screens can display over 1 billion colors and achieve 100% color accuracy on professional-grade monitors. OLED technology, for instance, is known for its ability to produce true blacks and infinite contrast ratios, while LCD screens use backlights to illuminate pixels. The role of brightness levels and contrast ratios also plays a big part in how we perceive images. High dynamic range displays allow for deeper blacks, brighter highlights, and a broader range of colors, enhancing the realism of visuals. The brightness of a display is measured in nits, with standard screens operating at around 300 nits, while HDR-capable screens can reach 1,000 nits or more for an exceptional viewing experience. While most screens today rely on liquid crystal displays, LCDs or organic light-emitting diodes, OLEDs, new and emerging technologies such as MicroLED, QLED, and e-ink are shaping the future of display innovation. These advancements aim to provide higher energy efficiency, better durability, and improved color accuracy, meeting the growing demand for advancing screen technology in everything from smartphones to AR and VR headsets. This is just the foundation of how displays work, but to truly appreciate modern screen technology, we must first understand how it all began. To do that, we need to go back to the 19th century, where the earliest forms of electronic displays were first noticed. In the next section, we'll get into the birth of display technology and explore how the world's first screens were created. While CRT displays led the 20th century, new and more advanced technologies soon emerged, changing the way we interact with screens. The demand for thinner, lighter, and more energy-efficient displays drove innovation, leading to the development of plasma, LCD, LED, OLED, e-paper, and DLP technologies. Each of these breakthroughs played a crucial role in shaping modern display technology. The first major innovation after CRT was plasma display technology, which was initially conceptualized by Hungarian engineer Kálmán Tihányi in 1936. However, it wasn't until 1964 that a team at the University of Illinois at Urbana-Champaign, led by Donald Bitzer, H. Gene Slotto, and graduate student Robert Wilson, developed the first functional monochrome plasma display for use in the Plato computer system. Plasma displays work by injecting inert gas or mercury vapor into a vacuum glass tube. When voltage is applied, the gas produces a plasma effect, emitting ultraviolet light that excites phosphors to generate visible colors. Unlike CRTs, which relied on electron beams, plasma screens could be thinner, brighter, and offer a wider viewing angle. By the early 2000s, plasma technology became the preferred choice for large flat-panel HD TVs, due to its ability to produce deep blacks, vibrant colors, and superior contrast ratios. However, it had several drawbacks: high power consumption, screen burn-in, and size limitations. By 2013, plasma displays were overtaken by low-cost LCDs and faced stiff competition from OLED screens, which provided superior contrast and color quality. Production of plasma TVs for the US market ended in 2014, and by 2016, plasma displays were completely phased out worldwide. The foundation of LCD technology dates back to 1888, when Austrian botanist Friedrich Reinitzer accidentally discovered liquid crystals while studying cholesterol benzoate in carrots. However, it wasn't until the 1960s that scientists found a practical application for this discovery. In 1962, Richard Williams, a physical chemist at RCA Laboratories, experimented with liquid crystals and observed that applying an electric field could manipulate their structure. This led to further research by his colleague George Heilmeyer, who developed the first functional liquid crystal display, LCD, in 1968. LCD screens work by sandwiching a liquid crystal cell between two parallel glass substrates. A thin film transistor, TFT, is placed on the lower substrate, while a color filter sits on the upper one. By adjusting electrical signals, the liquid crystals control the passage of light, creating an image. These screens gained popularity in the 1970s, primarily in calculators, digital clocks, and watches. However, it wasn't until the 1990s that LCDs became the chosen display for notebook computers due to their low power consumption, thin design, and lightweight structure. By 2007, LCD televisions surpassed CRT TV sales worldwide for the first time, marking a new era in screen technology. LCDs continued to evolve, incorporating LED backlighting to improve contrast, brightness, and color accuracy. In 1962, Nick Holonyak, an engineer at General Electric, invented the world's first visible light LED, light-emitting diode. LEDs quickly gained traction due to their energy efficiency, durability, and ability to produce bright colors. Between 1962 and 1968, Howard C. Borden and Gerald P. Pagini of Hewlett-Packard, named HP, developed LED technology further. In February 1969, HP launched the HP Model 5082-7000 calculator, the first device to feature an integrated LED display. This marked the beginning of LED's role in digital display technology. While LEDs enhanced LCD backlighting, the true revolution came with OLED, organic light-emitting diode technology. In 1987, chemists Deng-Ching Yun and Stephen Van Slyke of Eastman Kodak developed the first practical OLED display. Unlike LCDs, OLEDs do not require a backlight. Instead, they use organic compounds that emit light when an electric current is applied. This allows for deeper blacks, higher contrast, and faster response times. Since the launch of the iPhone X in 2017, OLEDs have dominated the smartphone and premium TV market, with advancements in foldable, flexible, and rollable screens. OLED screens are now widely used in smartphones, gaming monitors, televisions, and even wearable devices. The future of display technology is heading toward holographic screens, 3D projection, AR and VR advancements, and ultra-flexible foldable displays. Holographic displays, which project 3D images into the air, are being developed for use in entertainment, medical imaging, and even interactive advertising. Companies like Looking Glass Factory and Sony have already introduced prototype holographic displays that require no special glasses. In the next 5 to 10 years, we could see this technology become mainstream, replacing traditional 2D screens in certain industries. 3D projection technology is making its way into commercial spaces, allowing objects to be displayed in midair without the need for a physical screen. This could revolutionize museums, retail stores, and home entertainment systems, providing an immersive experience unlike anything seen before. Augmented reality, AR and virtual reality, VR screens are set to transform gaming, education, and remote work. With companies like Meta, Apple, and Microsoft investing billions in AR and VR development, we can expect lighter, higher-resolution headsets with ultra-realistic displays. Apple's Vision Pro, set for release in 2024, features micro-OLED screens with over 23 million pixels per eye, setting a new standard for immersive displays. From the glowing tubes of early CRTs to the incredible precision of OLED and micro-LED, display technology has redefined the way we see and interact with the world. Over the past century, screens have evolved from bulky, power-hungry devices to ultra-thin, flexible, and even rollable innovations, pushing the boundaries of what's possible. As we look ahead, the future of displays promises even more technological advancements. Holographic projections, immersive AR and VR experiences, and next-generation ultra-flexible screens that could redefine communication, entertainment, and beyond.